Okay, looking at these answers, the atomic mass, which is the total mass of an atom, is numerically equal to protons plus neutrons. The protons is the atomic number. Okay, so protons plus neutrons. Now, some people might have said, well, what about electrons plus neutrons? You can have an ion. An ion does not have the same number of electrons as it has protons. And it always needs to be protons plus neutrons. So in the case of an ion, electrons plus neutrons is not going to be equal to the atomic mass. Number 2, which of the following is not a chemical change? Bryson? Boiling water. I said Bryson because it was his question. Are you sure? That was yours too? Yeah. I was sure it was Bryson's. Okay. Burning wood is a chemical reaction. That's a chemical change. You have oxygen and whatever the fuel is that we haven't talked about yet undergoing a reaction. Rusting, these are all examples that we talked about in class. Rusting is, again, oxidizing of iron, so it's a chemical reaction. Mixing salt and water, the salt and water dissociate, or the sodium and chloride dissociate in the water so that they're no longer bound together. Okay, Hannah, this is yours, right? That's yours, Jessica? Sulfuric acid, H2SO4, is an example of now this one here, we didn't talk about sulfuric acid, but we talked about the definition, so it was fine. If it did, I made sure that I remembered to put that in there so it would be clear. So let's just make sure we know, what is a molecule? A molecule is a single unit of atom or atoms bound together. That's what I was looking for. H2SO4 actually would qualify as a molecule. So if you put that, I'm going to give you credit. That wasn't the intended correct answer. But it does qualify as a molecule. Is it B? B was the intended correct answer. It's a compound because it has three different types of atoms in this case. Hydrogen element, sulfur element, and oxygen element. Is it an atom? No. It has a total of 7 atoms. Let me get the last one. And is it an element? No. An element would have only one type of atom. Okay, Grace.
So why does it qualify as both? Okay.
Why is it? Because a molecule is atoms that are bound together as one unit. And since sulfuric acid, H2SO4, is bound together as one unit, it's a molecule.
Because there's not like a number in front of it.
No. Well, yeah, if it was 2 H2SO4, then it'd be 2 molecules.
Then it would have to be a compound.
Well,
and not a molecule.
Right, because it'd be multiple molecules, the singular would make it incorrect.
But since it's 2 different things, it's a compound and a molecule.
Right, well, it's 3 different, but yes, anything that's 2 or more elements is a compound. So the goal here was compound, but if you put molecule, I will not mark it wrong because it's also a molecule. Okay, last one. Where are the noble gases found on the periodic table? Okay, C, the far right column.
I changed my answer.
To that?
Huh?
To that?
No.
Oh.
I would have had a
Sorry.
perfect score.
That would have been nice.
Dang.
Yes,
So,
Amber.
A molecule, like a compound can't be a molecule, but a molecule can be a compound, right?
A molecule is atoms bound together. So a molecule can be an atom, or it can be an element, or it can be a compound. Understand? Okay. So any questions about the quiz? Did it go well? Good. No. I want them to go well.
I missed one.
Oh,
I put for number 1. Number.
I obviously won't check in front of everyone and tell you what you did.
Honestly, I don't even care.
I would.
Literally.
It would
my life.
violate your trust, even if you didn't care.
I don't think so.
This point, we can all know.
All right. We are going to cover chapter 15. And just to make sure we don't have the fiasco of Friday where we had to spend 15 minutes doing homework, I got like 45 slides here. We will not run out today. Yes.
So, hey, I have a question.
Yeah.
What happens when you miss a lab?
Well, you have to make it up.
Are you missing this one?
Yeah.
We are too, so just make it up with us.
Wait, why are you guys? I will be here on Thursday.
Neither will we.
I will be taking my praxis again. Yes, again. Why are you taking my praxis? Because it's a
limited
5-hour test.
Yeah,
What
let's-
other day are you gonna take?
those of you who won't be here on Thursday, talk to me after class because I got to make sure I have chemicals when you're going to come to take it.
Oh,
Okay, so electron dot structures, otherwise known as Lewis dot structures. Is a way of showing the valence of atoms. Remember on the periodic table you're going to have in the exam, it has the valence listed. The valence is an important thing. It's the number of electrons that can be used to form a bond. And so the electron dot structures or Lewis dot structures show us the valence. They show us the number of electrons that can be used to make a bond. So remember, we looked at a picture like this that I told you, this isn't real. This is a model, right? The electrons aren't in these nice concentric shells. But in the lowest shell, you have 2 electrons. The next one, 8. Okay, let's change to a color you can read.
Why don't they show us any pictures of real atoms?
Well, we did have, I think, one that showed like an atom with a d orbital, but it's, well, people used to believe it was like this, but it's because the model makes it easier for us to understand. And it's not like it's done just for your level. It's done for every level. You know, because it's to make it easier to understand the idea. So we have 2 electrons in the first shell, 8 in the second, 8 in the third, 18, 18, 32, 32. If you didn't know those numbers, how could you figure them out when you're taking the test?
Are you gonna be like giving us some diagram of it?
No. What you could do is you could turn around or look at your periodic table. How many elements are on the first period? That's because there's 2 in the first shell. How many on the second period? 8. Because there's 8 in the next shell, 8 in the next one, 18 in the next, and so on. These numbers here are essentially telling us how many elements are in each period. So it's not some sophisticated, hard to do math. Now, the electron dot structure is showing the electrons in each shell, except for, like I said, we ignore all but the outermost one. Only the outermost shell is going to be doing any kind of bonding with other atoms. So the behavior of an atom just depends on its outermost shell. So this is looking at the top 3 noble gases, helium, neon, and argon. Helium has 2 electrons in its outer shell, and so it has a circle with 2. And then, now in this case, those 2 are grouped together. We call it a pair. The reason they're grouped together is because that's all of the electrons that you can have in that shell. And so if it's complete 2, you have a complete pair and you're done. That's the only one that is done that way. We go down to the next one, neon. We still have the 2 electrons in the inner ring that nobody ever draws. But then in the next ring, we have 8 electrons. And notice that the 8 are paired up 2, 2, 2, 2. When you put those electrons in, for anything except for hydrogen and helium, you're going to start by putting 1, 1, 1, 1, and then you pair up if you have more. And so this had them paired up. You go to the next one, and we have the same structure in the outer shell because it also had 8. So we're just not going to look at this stuff in the inner shells. We're only going to look at the stuff in the outer shell for our electron dot pictures. Here is looking at chlorine and carbon. So chlorine and carbon, they're both not in the first period. Because they're not in the first period, we're going with 8s. Now, obviously, if you go down to the 4th period, it's a little more complicated, and we're not going to really confuse ourselves with that. We're going to only look at the 4th period as if it has 8, even though it has 18. So chlorine here is in our 3rd period. It has 8 electrons in the outer shell. And so if you look at the chlorine, it's in the 7th. It's in the next to last column. So it's missing 1 electron of having the full 8. So when you put the electrons in, you go 1, 2, 3, 4, 5, 6, 7, and you're left with 1 lone electron. But notice how I went around the circle to put them in. I didn't go 2, 2, 2. I went 1, 1, 1, and went around the circle. Now with carbon, carbon is 4 from the end, so it's missing 4 electrons. Remember, why is it missing electrons? Because a neutral atom has the same number of protons as it has electrons. And so you have a total of 8 electrons in the 2nd period, and you have 1, 2, 3, 4 across in the 2nd period. So you're going to have 4 electrons out of the 8 possible. And so for the carbon, I put 1, 2, 3, 4, and I'm left like that. Now this carbon has 4 single electrons. Each of those single electrons is out there looking for a match. It's looking to bond with something. So this carbon is looking to make 4 bonds. How many bonds is the chlorine looking to make? Not 7, because it's just the lone electrons, and it only has 1 lone electron. So it's looking to only make 1 bond. So these dots, they're representing electrons in the outer shell, and they tell us about how many bonds it's looking to make. Krypton is in the noble gases, so it's got the complete octet.
It's not
Notice,
a green rock.
It's what?
It's not a green rock.
Apparently not. I know, Superman, right?
Oh,
I did not know that Superman was not based on fact. So Krypton, it is a noble gas. Has 18 valence electrons, but only 8 are typically shown. Remember, I said that a number of times. So we only have 8 shown. We don't show the other 10. So here's electron dot structures for the elements that we're actually going to deal with the most. So we have the first column. What's the name of this first group? This was one of the questions submitted that made it through to could be on the test. Alkali metals. What's this second column? Alkali earth. And I'm going to drop off the word metal. It is, our textbook said alkali earth. It is alkali earth metals. So we drop off, this textbook's dropping off the word metals just to save us the confusion. Notice what's missing here is the transition metals. And then we have, you don't have to have this memorized, but our textbook specifies that this set here, I'm probably spelling this wrong. Chalogens, I'm not sure if it's 1L or 2. It's probably 1. That's probably right the first time. And then this one here, you do have to know. The halogens. And the last one, of course you have to know because that was on the quiz today. Noble gases. And notice the dot pictures. All of the alkali metals have the same dot picture, single dot, because they have one lone electron in the valence shell, in the outermost shell. The alkali earth all have two dots because they have two electrons in the valence shell. And then we get over to the chalcogens. They all have two lone pairs. Well, okay. I'm going to zoom in so you can see what I was circling. They all are two lone pairs, two lone electrons. They have the pairs out here. Those pairs are just going to hang out. They're happy. But the lone ones are looking to bond. And so the chalcogens all are looking for two bonds. The halogens, one lone electron, they're looking for one bond. And of course, we go over here to nitrogen. How many bonds is it looking to make? 3, typically. Phosphorus, 3. Carbon, silicon, 4. Aluminum, boron, 3 again. So you're not going to have this graph or this picture on the exam. This is stuff that you have to be able to deduce from the positions in the periodic table. Grace had a question.
Why is helium not follow the rule?
Because it is in the top one that only has 2 electrons. So it's completely filled, but it only has 2 electrons. Right, so helium and hydrogen don't have 8 in the outer. The rest of them, even though...
So it's completely filled, so that's a...
Helium's completely filled, yeah, so it's inert. Hydrogen, not completely filled, it's reactive. And remember, these things down here actually have 10 more electrons that we just don't show. All right, here's a question. Get out your clickers we don't use. Sodium, atomic number 11. How many electrons should it have if it is neutral? If it's a neutral atom, how many electrons should it have? It has 11 if it's atomic number 11. 11, right. Because if it's neutral, it's going to have the same number of protons as electrons. But it has that one valence. It had one dot in our picture. And the whole reason for this theory and the reason we do the dots is that when you have a completed shell, it's much more stable. So sodium, if you take away one electron, then it's a completed shell and it's very stable. Well, which element is sodium's electrons going to look the same as if you take away one electron? So it only has 10 electrons. Neon. Oh, I heard helium. Like helium only has 2. Yeah. Neon. It would look like neon with 10 electrons out there. And so sodium is very happy to give up that extra electron and just hang out as a sodium plus 1. It has a net charge of 1 more proton than electron. On the other hand, if you were to go to fluorine, fluorine has 7 electrons in its valence shell. How many would it like? It would like 8, so it's missing 1. And so fluorine really, really wants another electron. And so it's going to really try to pull electrons from somewhere. So it's very highly reactive because it really wants to have that extra electron. And we're going to get to actually a number associated with that before the end of the day. So ions are formed when you have electrons taken away or added to an atom. So we have here a picture of sodium with its 11th electron, and then a sodium ion where that 11th electron is missing. But this here has a net +1 charge now. Now, if I have something that really wants that extra electron, such as, for instance, fluorine, fluorine will latch onto that electron. And what's the charge of the fluorine going to become when it grabs that extra electron? It's 0. It grabs an extra electron. What's its charge going to be? -1 electron. So the fluorine is going to become negative if it grabs that extra electron. The sodium becomes positive when it gives it up. Now, we usually don't talk about sodium and fluorine. We talk about sodium and chlorine. The chlorine and the sodium then, one has a +1 charge, one has a minus charge. What kind of force do I have between a positive thing and a negative thing? Electric charge. Attraction, because opposites attract. Likes repel, opposites attract. Protons are repelling other protons because they're both positive. But if I have a positive atom and a negative atom, they're going to attract to each other, so they're going to bond together. And so we call that kind of bond, so here showing fluorine like I was talking about, fluorine wanting to fill that extra space but now having a -1 charge. So if we let them come together, I don't know why I left these pictures in. I'm going to skip 2 pictures here. If we let them come together, and actually I do have the sodium and fluorine here, I'm going to have them held together because they're ions, and Coulombic force holds them together. Coulombic force is what we learned with electricity, that opposites attract. And we call this an ionic bond. It's an ionic bond because I had ions, things that had a charge, one's positive, one's negative, held together because of that charge. So in a very practical sense, I have a sodium and a fluorine. And the sodium says, you know, I've got this electron that I really don't cherish. And so it has this electron and it says, I'm going to let it go. The fluorine says, I would love to have that electron. And so then I end up with the fluorine has the -1 charge because of the extra electron. Sodium has the +1 charge. And the 2 charges, opposite signs, attract each other. That's an ionic bond. Does that make sense? It's the one that to me makes the most sense. So I'm hoping that that one makes sense to you. We're going to go through and talk about covalent bonds and polar covalent bonds before the day is through. So when we make a molecule, we probably want to make a neutral molecule, just like we want to have neutral atoms. And so here is a kind of tough question. What's the chemical formula if we want to make a neutral compound that's made of aluminum? The aluminum is happy to give up 3 of its electrons, so it has a +3 charge. And oxygen really wants 2 more electrons, so it's going to have a charge of -2 if it can. What compound can we make that's going to have a net charge of 0 out of those?
D.
Okay, let's just go ahead and calculate all of them.
C.
Anyone want to go B? It is C, by the way. Anyone want to go B? Let's calculate the charge. Aluminum has a charge of +3, and oxygen has a charge of -2, but 3 minus 2 is equal to 1. So it's not A, because A would have a charge of +1. If we go to the next one, we have 3 of these +3s, plus 2 of the -2s. 3 plus 3s is +9. 2 minus 2s is -4. 9 minus 4 is +5. That one's way off. No one answered that. Here we have 2 of the +3s, plus 3 of the -2s. 2 times 3 is 6. 6 minus 6 is 0. And then the final one, 6 plus 3s plus 6 minus 2s. That's 18 minus 12 is 6. So in order to get a neutral charge, it had to be Al2O3. Now, trivia question. Anyone know what Al2O3 is? Okay. Aluminum oxide is a correct answer. Using the rules that we learned in class on Friday.
Diammonium trioxide.
If there were other,
That's pretty good.
yeah, if there were other things that would be, in the state, there's a very simple word for it, not unique. But if there were oxygen compounds, that would be, because there aren't, we don't have to. It's never going to be wrong. Okay, and aluminum oxide, aluminum is farther to the left. The actual rule is the one that is giving up electrons, is the one that we should do first. So the aluminum is the one giving up electrons, that's why it's first. Oxygen is the one getting electrons, that's why it's second. And then we change the oxygen to oxide. So Jessica showed clear command of this rule, which is good.
Yes, I am a chemist in my free time.
You what?
I make up these words in my free time.
Oh, well, good. So there are some other names for this. Sometimes we just call it alumina. If it's a polycrystalline form, we will call it something like corundum. Or if it's a single crystal, we call it sapphire. So that's what sapphire is. It's just aluminum and oxygen. Now everybody knows aluminum is a metal. And then you look at sapphire, you're like, sapphire is a whole bunch of metal? Yes.
Okay, I have a question. My people said that I couldn't, like, if I had something metal in my carry-on, I have to take it out when going through TSA. That's not true. If it's packed in my carry-on, it's fine as long as it's not like.
I don't know TSA's rules in and out, but I'm pretty sure that's not true. You're correct.
Yeah, right?
Now, on the other hand, if you have a knife and it's metal, you have to take it out.
Well, yeah.
If you have a knife and it's ceramic, you also should take it out, just for the record.
Thank you. I will be sure to take out all my ceramic.
I know one young lady, we'll call her Amy Webb, who forgets these kinds of things. And we get stopped by TSA more than we go through without getting stopped. It's interesting.
That sucks.
Oh, big kitchen knife like this in her carry-on. Yeah. Okay, so it's called sapphire. Here is,
Why don't you have a kitchen knife in our carry-on?
because she wanted to peel, I think it was an avocado while we were flying.
Should she go down to her check bag? And
Yeah, she was able, we were there early enough that she was able to go and get it into her check bag. We have had other things confiscated.
you can take a butter knife. Just for future. You can also take like turkey sandwiches if you get hungry.
Can you carry it?
Yeah.
You can take all kinds of
You can
food.
take
I just can't take liquids. I always bring chocolate milk for TSA.
Yes.
Yeah. Taco Bell, yeah. And
Okay, let's get back to chemistry.
Taco Bell is chemistry because sometimes you eat.
Okay.
I know what kind of chemistry.
Sapphire. I want, what does sapphire look like to you? When you think of sapphire, okay, you said blue. What? Pretty? Now, I did my research. My master's degree research was studying sapphire. And sapphire is a very clear glass. Probably didn't know that, huh? Because we never see sapphire that's pure. We always have impurities in it. And so if you put, for instance, chromium impurities in it, this is Al2O3 sapphire with chromium impurities. And the chromium gives it that pretty blood color, and we call it a ruby in that case. And if you put other impurities in there, you can get different colors. So what you think of as a sapphire, the gemstone sapphire, is not pure. It has impurities to give it its colors. And the sapphire is held together by ionic bonds. And so you just have these aluminums and oxygens sticking together because of their charges. So remember, ionic bonds, they're held together because you have positives and negatives and opposites attract. Now, metal bonds, this is the only thing we have on metals. Metals are the trickiest type of bond. I didn't even mention it when I said we were going to talk about covalent and polar covalent. I didn't even mention the metals. Metal bonds, metal atoms, things that are in the transition metals there, things like copper, nickel, iron, gold, they have their valence electrons so weakly held that essentially the electrons will become dissociated from the nuclei and just travel around freely in the metal. That's why metals conduct electricity. And the metals are held together then because of the charge of the electrons moving around freely, a net negative, and the positive charges of the metal atoms. One of the unique things about the metal bond, though, is it's not really a bond from atom to atom. It's electrons and atoms. And so you can very easily put in other atoms, and the metal doesn't care. And so we call that alloying. And alloy is where you take a metal and you mix in another kind of metal with it. So the example here is the Sacagawea dollar. It's a coin that looks gold. Is it gold? No. No, it is not. But it looks gold. And it's made by putting in 77% copper, 12% zinc, 7% manganese, and 4% nickel. So it's mostly copper. But you have these other metals, and when you put them all together, it gives it this unique color. Yeah.
How is it? Well, I hear that copper is really expensive, and so someone I knew was working on. They were developing houses. They had problems with people coming in and stealing copper wiring.
I don't know the value, but I know that does occur. You even have the crazy cases where people will go and steal wires from high power lines. You have to be really careful to not kill yourself in that case.
Yeah.
And it doesn't seem like it should have that much value, but I guess you get enough of it. But I don't know what its value is. Okay, now moving to covalent bonds. Now we talked about valence electrons. Valence electrons are the ones that are available. Covalent bonds are bonds that are made by sharing available electrons, by sharing valence electrons. So an example of a covalent bond is here when you have two fluorine atoms. Now each fluorine atom has 7 electrons in its outer shell. It would like to have 8. And so what they do is they say, okay, I'll kind of share mine with you, you kind of share mine with me, and we'll both feel like we have 8. And so that's what a covalent bond is when the electron is shared between them. So here we have the Lewis dot structure, the electron dot structure, showing 2, 4, 6, and these two make 8 for this one. 2, 4, 6, and these two make 8 for that one. They both are feeling like they have their full octets. And so that's a covalent bond. Now, covalent bonds, you have shared atoms. There's a direct bond between atoms. So when we draw atoms that are bonded together by covalent bonds, we draw a line between them to indicate the covalent bond. So this here is the normal way of drawing a fluorine molecule. Fluorine molecule is F2. It's 2 fluorine. Okay, I say fluorine molecules. Is it a fluoride molecule? Yeah, I think. Well, it probably is a fluoride molecule. But it's 2 fluorine atoms bonded together. And so we write it chemically as F2, which you see right there. It's F2, but if we show the bonds, we show F bonded to F. And then here's the electron dot structure of that bond. This is called covalent. Why is it called covalent? Because it's sharing the electrons. Question, Grace?
How do you know, like, when you're making your bonds and stuff, if you're like, oh, we're going to bond this element with this element, how do you know if it's covalent or... That is
a perfect segue. How do we know? Okay, I've got a couple slides and then I have the answer. So this is just showing covalent bonds between hydrogen and oxygen to make water. Now, if you look at the water, the oxygen atom has 6 valence electrons. So just like we said before, you put them in one at a time, and you have 2 pairs and 2 lone electrons. So which electrons are going to bond? The single ones. So I'm going to have 2 electrons that are available for bonding. This one and this one. I'm going to have excess negative charge for those 2 sets of electrons that aren't bonding to anything. And so what's going to happen is I'm going to have a structure that's not flat because of that negative charge. So you have the negative charge out here pushing the hydrogens away to give you a water molecule, as I said in class yesterday, that's somewhat like this.
Well, it's actually bent, so it's like a 9. Well, I mean, I guess that's still.
It's like 109, I think. Now, in terms of charge, did the oxygen want more electrons, or was it looking to give up electrons?
Wait, say it again, I'm sorry.
Did the oxygen want more electrons, or was it looking to give up electrons?
Oh, definitely.
The oxygen wanted more electrons because if it adds 2 more, it's complete. You'd have to give up 6 to get complete, and that's a lot. So the oxygen wants electrons. The hydrogen has 1 electron. It can go either way. If it loses 1, it has a shell of 0. If it gains 1, it has a complete shell of 2. So the hydrogen can go either way. So in this case, since the oxygen really wants the electrons, what's going to happen is the electrons are going to spend a lot more time over here and a lot less time over with the hydrogen atoms. So the hydrogen atoms are going to behave kind of like they have a positive charge. Now this comes back to what Grace said. How do I know the difference then between a covalent bond and an ionic bond? Because an ionic bond would be held together if you have the positive and the negative. Covalent is if the electrons are shared. How do I know which one it is? Well, the answer comes from looking at how strongly they want electrons. So we're going to have, oh, yes, I told you a couple slides. Here's the other one. This is ammonia. So ammonia is a nitrogen with 3 hydrogens. See, the nitrogen has, great. The nitrogen has 3 lone electrons. So it can make 3 covalent bonds, 1 with each of those. It has a single pair of electrons hanging out by itself. And so it's going to, again, have the hydrogens down kind of like in a pyramidal shape below the level of the nitrogen because of charge distribution. Okay. Oh, wow. And then there's methane. Methane is a single carbon with 3 hydrogens attached to it. Methane is very flammable. It can be easily oxidized so that you burn it. You break the hydrocarbon, in this case CH4, into smaller things. Why do I have methane after ammonia and water? The oxygen had a valence of 2, the carbon a valence of 3, or the nitrogen a valence of 3, and the carbon a valence of 4. So it's showing those. Okay, so I want to get to the answer before I go too far. The answer is in the electronegativity. Electronegativity is how strongly the atom wants another electron. So fluorine really wants another electron. It's the most electronegative. Whereas hydrogen, it's happy to give up an electron. It's not very highly electronegative. So here is a graph, a periodic table, that shows the electronegativities of different elements. And so you see francium has a very low electronegativity, 0.7. Francium really doesn't care about its last electron. Jessica?
Can you go back for like 3 seconds?
3 sentences?
Seconds.
Like to the last slide.
Yes.
To here?
Okay, I'm good.
Okay. So francium down at the bottom left, really, really easy to take an electron away from it. Fluorine up here in the top right, 3.98 for its electronegative. That's the most electronegative of all of the elements. Fluorine wants electrons more than anything else. And so the higher the electronegativity, the more pulling power for electrons, as it says here. And so if I mix things, like if I take hydrogen and fluorine, the hydrogen has 2.2 for its electronegativity, the fluorine has 3.98. There's a difference there of 3.98 minus 2.2 is equal to 1.78. That's the difference in the electronegativities. That's what we look at to determine if it's going to be an ionic bond or if it's a covalent bond. So here is the rules for that determination. If the difference in electronegativity is bigger than 2, then it's going to be ionic. If the difference is between 1.6 and a half, then it's going to be what we call polar covalent. Polar, one side is going to be more positive, one side is going to be more negative. And if the difference is less than a half, then it's going to be non-polar covalent. Where it's, remember, we learned about electric dipole moments. Well, that's where they're going to come from and naturally occurring when you have a polar covalent bond or an ionic bond. Those are polar compounds. Notice that there is a gap. 2 to 1.6 is a gap. That's kind of an indeterminate range. It's somewhere between polar covalent and the ionic. And in fact, if you want to get really technical, everything except for a perfectly non-polar covalent bond, like fluorine and fluorine or oxygen and oxygen, is some combination of ionic and covalent, right? So the ionic and polar covalent and covalent, they're names that really work for us, but in reality, it's a spectrum. It's kind of like autism. You have a spectrum. You don't just, not all autistic people are the same. Okay, now let's come back to what we skipped. So here are some examples of non-polar covalent bonds. Oxygen and oxygen. Now that we've looked at the electronegativities, it's pretty obvious oxygen has the same electronegativity as oxygen. So the oxygen molecules or atoms are each pulling electrons with the same strength. The charge is going to be symmetrically distributed between them. That's got to be non-polar, not one positive side, one negative side. The carbon dioxide, carbon is going to form because it doesn't have any extra electrons after it forms these bonds, it's going to form a straight linear molecule. And in this case, the charge will be symmetric. You will have a negative on the left and a negative on the right because oxygen wants the charge more than the carbons. But if it's negative on the left and right, then it's still symmetric. And so it's non-polar. And then the nitrogen is just an example. Notice it has 3 bonds for the nitrogen, 2 bonds for these others. You can share more than one electron. So when oxygen bonds with oxygen, you're having 2 electrons shared from each atom, which kind of breaks our electron dot structure, right? Because we're taking those 2 electrons we had for oxygen like this, and then each one of these is forming a bond with the next oxygen. It's not a violation, but it looks a little different. There's an example of hydrogen. With fluorine and hydrogen, because the fluorine is more electronegative, you have more negative charge around the fluorine atom, and hence it has a negative side and a positive side. So with the water, do I have another picture of the water? Yeah. With the water, and I will end with water, because the oxygen is more electronegative, it pulls the charge over. So you have a negative charge. It says negative delta here. That delta is about 0.75 electron charges. So the oxygen behaves like it's a net about minus 0.75, and each hydrogen, actually it's 0.7. Each hydrogen acts like it's a net positive about 0.35. That's important because that's why ice is special. Remember, ice is special. It grows when you freeze it. It's because when you freeze it, you will have the molecules align. So that's supposed to be an H. So that you have the positive H here forms a bond with that negative O. We call it a van der Waals. Solid. So liquid, it's randomly oriented, and solid, I don't have here's the picture for the solid, but we'll have to pick up on that
Can you go back to the last
Wednesday.
slide that you were on?
This one? All right, have a great day. And remember, those of you who won't be here Thursday, make sure you stop and talk to me right now.